Hello, this is a video on hand calculations and it's going to focus on Vierendeel girder. This is the 6th video in a series and will only really make sense if the previous videos have been worked through. The aim of this video is to show how to carry out an approximate analysis of a Vierendeel girder, so best of luck. Here we go. So in previous videos we've looked at stiff beam frames, frames with pinned feet, single story frames with pinned feet and constant EI, single story frames with fixed feet and constant EI, and multi-storey frames and quite significant multi-storey frames. Now we're looking at a Vierendeel girder, which is slightly different but a very similar approach. So here is an incredibly simple Vierendeel girder. It's 4 bays of 4 meters each, 4 meter high, and it's a 100 kilonewton single point load applied at the center. Each of the members has a constant EI, which you may argue may not reflect reality. However, it does occur because here's a nice bridge, one of my favourite bridges, which shows that it's broadly constant EI throughout the bridge. And how are we going to approach this? Well, it's a similar approach to frame structures in that we focus on the shears within the members, we focus on points of contraflexure, and we create subframes which we find are simple to analyse, and then we combine the results to create the entire bending moment diagram. So here is the Vierendeel girder with 100 kilonewton point load. It's a symmetrical structure, so I'm expecting that each of the vertical reactions at each end of the frame will be 50 kilonewtons from the 100 kilonewtons. Right, how does that 100 kilonewtons travel through the structure to the supports? So what's the load path for that 100 kilonewtons load? Well, because the upper chord is equally as stiff as the lower chord, I'm expecting that the load will travel equally along both of the chords to the points of support. So of the 100 kilonewtons, so if we just look at the left hand side now, there's 50 kilonewtons heading to the left. So I'm expecting 50 kilonewtons, 25 kilonewtons to travel along the top chord and 25 to travel along the bottom chord. So this means that there'll be 25 kilonewtons shear force transmitted along the entire top member until it reaches the very first vertical member, and then that will transfer to become a 25 kilonewtons axial compressive force down to the support. And then at the center of this 100 kilonewtons, half of that 100 kilonewtons travels along the top chords, and the other half, 50 kilonewtons, comes through axial compression down the central member, and then through shear it's carried to the ends. It's carried in bending and shear actually. Yes, there are axial forces within all of these members which are of interest, but the forces that I'm really interested in this analysis are the shear forces that are transmitted along the members, which create significant bending moments within the members, and particularly at the joints. So you can see that there's a kind of equals approach here. So this 100 kilonewtons is shared out both sides equally, and it's shared out top and bottom equally. So that means that I know that I've got this 25 kilonewtons shear, 25 kilonewtons axial compression, and 25 kilonewtons shear. Okay, that's important to kind of have a feel for the way that the forces flow through the structure, especially when you're as good at drawing deflected shapes as I am. Right, so here is a deflected shape with points of contraflexure noted. So wherever I have a beam or a column that's fixed at each end that may be subject to rotations or differential movement or bending moments, which could be a result of both of those situations, then I'm expecting some form of contraflexure to occur. I'm expecting the bending moment to take a form so that the tension face changes from one end of the element to the other. Okay, so as this entire girder is made up of fixed ended members, you might expect that every single member has a point of contraflexure. Well, it probably would do, except that in this very strange situation, because there's no bending moment, because it's a single load case and it's a single load, there actually is no bending in the central member. That's just a kind of quirk of this particular setup. Right, so now we have points of contraflexure at the centre of each of these elements in the Vierendeel girder, so we can cut the structure up how we choose. We can create lots of little subframes and work on them as we go. So how am I going to do this? I'm going to start at the left hand side with a little subframe there at the support. So I know that I have a 50 kilonewton reaction at the support, and I also know that this member, this vertical member, carries, it must be carrying, because I've worked that out earlier, a 25 kilonewton axial force. Okay, and I've also said that along the bottom of the member, the bottom chord is in shear to the tune of 25 kilonewtons. Right, so if that member's in shear to the tune of 25 kilonewtons, I can now look at this bottom member and say, well, that looks very much to me like 25 kilonewtons fixed here, pin here with a point load of 25. They're 4 metre bays, so this length here is 2 metres. Therefore, the bending moment is going to be tension on the top here as that bends down. So the bending moment is going to be simply 25 times 2, 50 kilonewton meters. So I'm going to draw in my bending moment there of 50 kilonewton meters. Okay, so I've got 50 kilonewton meters bending round like that, and now I know that if I take moments around this point here, the sum of the moments must add up to 0. Therefore, there must be some bending moment in this leg to the tune of 50 kilonewton meters, and that will occur due to the shear at the mid height of the leg. So there must be a horizontal shear here. This is 2 meters to there. There must be a horizontal shear here of 25 kilonewtons. 25 kilonewtons acting at this on this leg, which looks a lot like that, and it's a 2 meter length. So I end up with a bending moment down here of 50 kilonewton meters. There we are, I'll draw it in. 50 kilonewton meters. So now this joint is in equilibrium. If I resolve vertically, I see I've got 50 kilonewtons heading up, and I've got an axial force in the member of 25 and a shear force in this bottom chord of 25. And now I can move on. I could actually add in the axial force here by resolving horizontally. Now I'm going to move on to the next part of the frame. If I know I've got a shear force here of 25, I know I must have a shear force here of 25. I can treat this as a vertical cantilever, and I know I'm going to end up, therefore, with a bending moment there of 50 kilonewton meters. Once I know that this is spinning round by 50 kilonewton meters, I know that if I take moments around this point, this leg must be resisting that by 50 kilonewton meters. I already know that the shear force along the top chord is 25 kilonewtons along the full length of the top chord. So 25 times 2 meters, that gives me my bending moment of 50 kilonewton meters. Oops, there we are. So now that's how I've split the structure into some little subframes. There's a very small subframe first, that one, and then I've looked at this subframe, and now I can work my way along the girder heading rightwards. So now I'm looking at the members in the next bay along, the next two joints, and I know that the vertical shear in the top and bottom members is 25 kilonewtons. Therefore, I can work out the bending moments in each of these legs, Well, 25 times 2, because it's 2 meters to the pin at the point of contraflexure, 25 times 2 gives me a bending moment there of 50 kilonewton meters, and that's bending in this direction. And the same at the bottom. I'll take that down to there. That's 50. And again, that's bending round in this direction. How about the right hand leg? Well, I know again that I've got this 25 kilonewton shear in the top member, so I've got 25 here, 25 in the bottom member, so that's going to be a similar kind of bending moment. I'm going to end up with 50 kilonewton meters there, and this time it's bending round in this direction. So again, there we go, that's bending in that direction. So now what about the bending moments in the column? Well, the column must be resisting to the tune of 50 plus 50, that's 100. So there must be a bending moment in the column of 100. That means I have an internal shear in the column of 50 kilonewtons. 50 times 2 gives me 100. Okay, so that's going to create a bending moment diagram that looks like that. Similar in the bottom, I'm going to end up with a bending moment of 100, and that's going to be acting in this direction due to the internal shear force here of 50. Okay. Now at the very centre, where we have 0 bending moment in the vertical leg, we end up with this 25 kilonewton shear creating 50 kilonewton meter bending moments in the beams again, but this time with no corresponding bending moment in the vertical member. When you join all this together, you end up with a bending moment diagram that looks like this. This is a quite simple example, and I've gone through it quite slowly, and in the next video we'll be able to look at a more complex example of a bridge with more than a single point load at its centre. So I hope this made sense, and thank you for watching.